This example is a continuation of the first one that we ran, where we analyzed or wished to analyze the dissolved oxygen content in 3 different lakes. We have a simple graphical technique that we can use for investigating homogeneity of variances, and we'll look at a couple of approaches for what do you do when the data have heterogeneity of variances or are non-normal. So we begin our program the same as we've seen on the previous handout, where we have a display manager command that clears the log window and the ODS results. The title statement, the title that we saw used in the previous example, labeled the tops of the pages of our output with the name of the example or whatever information we wanted. Titles are global statements, so that even if you change programs within SAS and you'd never alter the titles stay put until you erase them or clear them, and so title semicolon clears all lines of title. Whenever you put an asterisk in the first space at the left side of a statement, that becomes a single line comment, and so the green color here on screen is an indication of that. I usually do something like this to help myself, so that if I'm looking at the program, this is how I have the program saved on my computer. So I go to Levene2 is the name of the program, and I can pick that information up. So that's just an optional thing you can do. On the previous example, we had data, input, and data lines as our data step, and I've modified this here in a couple of different ways. First, you'll notice the data go across the page rather than down in the column, because I did emphasize previously that if you put 2 variables on the input statement, then SAS is going to look for 2 pieces of information on every line after the data line statement, the first piece of information being lake and the second piece of information being oxygen. This is a short data set, so if you look back at that previous example, here, we boot it up a little bit. Okay, this is what we had before, and so it would take 30 lines to do this, whereas this, I did this in 3 lines. I repeated the lake information response, lake response, lake response all the way across. In order to get SAS to read across like that, you need these @ symbols, and it has to be both of them, and they're not separated by spaces, but that gets it to the cursor control to read across. And without the @ symbol, if you were to arrange your data like this, you would get only the 1, 0, 2, 1, and 3, 14 responses. @ allows it to read across. Just remember to repeat both the lake and the oxygen. You cannot put just lake 1 and then list all 10 observations for lake 1. That would never work. Okay, so that's another modification on the data. That reading across the page would still work if your lake were a character and you had the space and the $sign in there. In between the input statement and the data line statements, you can create new variables, and so in this I'm creating a new variable called A, B, and C. The creation of these new variables are SAS statements. Notice they are each punctuated on the right with a semicolon. What happens then is the syntax here is new variable equals and then a function of existing variables. And so the first I'm taking the log, this is the log base E, or natural log, of oxygen plus 1. You can't take the log of 0, so we're adding 1 to everything and then taking the logarithm. B is taking the square root of the oxygen content. Oxygen content is 0 and greater, so taking the square root is okay. If you had a response variable that had negative values, the square root could not be done. Variable C takes oxygen times oxygen, or squares it. And so that I wanted to show you what the effect of transforming the data is. So very often researchers will transform their data if the normality assumption is violated, and or the homogeneity of variance condition is not valid. Now you have to be careful whenever you choose a transformation, because the transformation you choose could exaggerate the problem, or it may not fix the problem, or it maybe you address the non-normality, but you don't correct the heterogeneity of variances. So here are just three such options. Other things you can do for transformations is you can look at reciprocal functions, other kinds of transformations, or where you take the response variable raised to a power. Some of you may be familiar with a Box-Cox type approach, and those are individuals' names. We talked about the print procedure before, and so the print procedure just prints the contents of the data set. The contents of our data set has changed. Not only does it have lake and oxygen content, but now it also has these values A, B, and C. And so that if we page down, go to page 2, so our original data set is modified in that we have these three new pieces of information, and so that those lines between the input statement and the data line statement then worked on every observation in the data set, creating new columns. So that's the result of the print procedure on page 2. Proc plot. This is a low resolution graph, not presentation quality or publication quality at all, but for the purposes of this course and having a quick peek at the data, it does a couple of things well for us. So I am using the plot procedure, and I'm operating on data set 1. Again, things that are uppercase or SAS commands do not change how they are spelled or punctuated. Things that are lowercase you can change to make problem specific. So in this plot procedure, then I use a plot statement, and then I have lake, by, and then these variables in parenthesis, and so it's going to create an XY coordinate axis, and so it's always vertical, asterisk, horizontal. So I'm going to get 4 different plots. I'm going to put 4 on a page since I'm dividing the page up vertically 25%, so that I'm going to get lake by oxygen, lake by A, lake by B, and lake by C. I'm creating vertical reference lines at 1, 2, and 3 to correspond to the 3 different lake values. And that information then appears on the handout page 3. I told you these weren't pretty pictures, but they help demonstrate some things really quickly for us. Lake by oxygen. So we see the concentration of the data points down here close to 0 for the first 2 lakes. Lake 3, all the data points then are over here further to the right. Where you see a B or a C, that means using this approach the data points are concentrated in an area, so we have a strike over, and so the farther into the alphabet you are is an indication of the concentration of data. So if you saw here an H, that's the 8th letter of the alphabet. That would be indicative of 8 observations at that point. So we see that the lake 3 values tend to be more dispersed than lakes 1 and 2 down here. Lake by A is in the second image, and this was whenever we took the log transform. We added 1 to everything and then took the log transform, and so that here we see we're just looking at the overall dispersion, high to low. Of course, the values of A here are going to be on a different scale than the values of oxygen. So it doesn't appear that this has really remedied the situation for us much. In lake by B, here at the top, we see kind of similar ranges of values from high to low for each of our lake, and so that taking a square root transformation, which is what B is, may be one possible alternative. Lake by C, C took and squared the oxygen content, and so here when you look at this, we made the problem worse by squaring that. So here F is the 6th letter of the alphabet, so we have this high concentration of points near 0, and then we took these very large values for oxygen in the original scale, and when we squared those, that range became even larger. So C is definitely a wrong approach. A didn't really address the problem, and B tended to be the best at it. So that we didn't get too repetitive here, I did not repeat the GLM procedure for the original oxygen response variable, but I've chosen proc GLM on dataset 1, activated all the plots that I wanted. Class is lake, so it's always your treatment in the class statement, and then response equals lake. Okay, and then I want to run the Levene's test again. So here the new B response is the square root. Did the square root transformation address the problem for heterogeneity of variances? And so then we'll look at the output then for this GLM procedure. So this does differ from what we had in the previous example, and so that we have the same class information, lakes 1, 2, and 3, 30 observations. So if we look at B equals lake for our model, it tells me right here the dependent variable is B, and I look at the type 3 analysis down here at the bottom. This is saying that there is a difference among the 3 lakes in the dissolved oxygen content means. True if I can make that conclusion if I've corrected the heterogeneity of variance problem. Fit statistics for B, we can see here similar ranges in the residuals vertically. We have a data indicated here that are approximately normal. We've got a little bit of a hitch in that normality right here, but not bad. And then our histogram of the residuals over here on the lower right. Box plot, we see similar ranges. So this is what I did before with the ABC plots that ran horizontally. This is capturing that same information vertically. Levene's test for the homogeneity of variances, and it tells me in this there's a B right here indicating that I'm no longer using the oxygen variable but the transformed value B, the square root of the oxygen content, and it's done then an analysis of variance on those absolute residuals. And so we find then that using the square root transform of the data, there is no significant variability in the variances of the 3 lakes. And again, it also has this redundancy with the box plot. Then we look here at the final table. These are the means, the y bars for the B variables, and then the standard deviations of each of those lake responses of the square root transformation. So you see more similar looking standard deviations than we saw with the raw data. Then we move to the mixed procedure, but before we do that, let's go and look at the program code for that. Prefacing this mixed procedure, it sometimes can be very difficult to find a transformation that fixes the problem. So we could make the problem worse. We could find a transformation that doesn't really help. We may not always find one that's better. And so how do you find one that's better? Well, what if you can't? The other challenge associated with transforming variables is interpretation. How do you explain that to someone? So typically, if you do a transformation such as we have here, you look at your transformation of say the square root of the oxygen content, you conduct your analysis of variance, and later we'll learn then more about how do we make further comparisons among the lakes, and you do the entire analysis with the square root transformation. You then at the end you recover the means and the standard deviations, and then you transform those back to the original scale for any report you write. It's not always easy to find a transformation that fixes the problem. So if it's just a heterogeneity of variance problem and normality does not seem to be an issue, we can do the following. The mixed procedure, we can operate on data set 1. I guess 1 should be lowercase here, and we request another plot that's a residual panel as one word. Our class treatment, generically, class is treatment. Our model is response equals treatment. And then I put a slash, and when you see a slash, and the things that come after it are called options. So I put a Satterth option on here. This is short for the name Satterthwaite. You may remember that from 5013 whenever we compared 2 treatment means and we had unequal variances. We had a Satterthwaite degree of freedom calculation. This is that same calculation though extended to generically T treatment levels. We use a repeated statement in this mixed procedure. The repeated statement then allows us to create multiple variances, and so we want a variance for each group, which is the lake variable, and then I want the least squares means for lake. And so this is an alternative then 2, transforming the data, and this is just saying, okay, we recognize that the variances are unequal. Let's use those unequal variances. Let's approximate the degrees of freedom, and then we'll make our comparisons. So we'll move then to the page beginning with the mixed output. This begins on on handout page 8, and it says up here at the top the mixed procedure that SAS would print there, in addition to the fact that I used titles to print the mixed procedure as well. We get a little more information at the top. SAS tells us it's working on data set 1, and it's using the oxygen response variable and the original variable, not a transformation. And that we're looking at our group effect was that from that repeated statement for lake, and then our degrees of freedom method here is Satterthwaite. So those are the important pieces of information. Again, in red here are the remarks I'm writing to you. For the class equals lake, we get the same sort of class information that we've seen previously. There are some tables in these output that may not always be meaningful to you, so the dimensions, we won't talk about it. Number of observations, we know we had 30 data points. What's going on with the mixed procedure is that there's a lot of information being computed, and in the background, and what we're looking for is this message that said convergence criteria met. If for some reason you have a program and you run it, the mixed procedure, and you see something else here, such as infinite likelihood, did not converge, so messages like this, and you have an incomplete analysis, then you've got a challenging problem there and you need to visit with a statistician. Sorry, there's not a more glamorous answer to that, but you need to get some more help with that, or some more training. So convergence criteria met, this is what I call the happy message. If we see the happy message, then we move forward. We used a repeated statement in that block of in that block of proc mix statements, and we indicated that the lake was the group variable, and so for each of the lakes then it computes a variance estimate. These look quite a bit different from what we saw at a GLM with the mean statement, because these are variances, and in that other in the first handout, whenever we looked at the output from the mean statement, the values were standard deviations, and so if you squared each of those, they should be they should match these values. Fit statistics, this is something we'll skip for now. With that repeated statement that you oftentimes will get this null model likelihood ratio test, there are some times whenever this will not print. But what it's testing here, what it is printing, is it's testing whether or not we have all three variances are unequal, or generically, do we need t variances, or can we use a single mean square error variance? So that's what's being tested here. So this is significant, saying that at least one of our variances is different, or that this multiple variance model is doing a better job than a single variance model. That kind of agrees with what we saw in Levene's test. If then, with that repeated statement in place, the type 3 test of the fixed effects, this is being computed by using this model statement, and we've enabled the Satterthwaite degrees of freedom. So you see this 12.7 here for denominator degrees of freedom, and that's that Satterthwaite calculation at work. If we had not done a Satterthwaite calculation and just used the regular analysis of variance, recall that our error degrees of freedom was 27. So the smaller this degrees of freedom is, that's the associated with a greater disparity or more unequal variances. And so that if the variances were very similar, this denominator degrees of freedom would be close to the analysis of variance degrees of freedom, which was 27 in our case. So that's computed an F statistic based on this 2 numerator and 12.7 denominator degrees of freedom and this p-value. So this is saying that using unequal variances and the original units in parts per million for the dissolved oxygen content, we're finding that there is a difference in mean oxygen content among the three lakes. If you want to see what the means are for each of those three lakes, then within the mixed procedure, use the LS mean statement. There is no mean statement in proc mixed, and so it is LS means, and you will see us in later examples for analysis of variance use a LS mean statement rather than a mean statement. And so what we look at in this estimate column, this is the mean dissolved oxygen content, and then the corresponding standard errors for each of those then appears here. These are unequal because we have unequal variances model, so you probably be accustomed to seeing all those looking quite similar. You can also request then a residual panel. Shrink our size down here a little bit. So I'm just looking at these three things here. We see that funnel shape there. We see the histogram indicating that we have a very symmetric looking distribution, and then our data appear to be normal because they do still coincide with that that vertical. Goodness, got it wrong all two times with the 45-degree line. And so there is some, we tried to address then this heterogeneity of variances and with our unequal variances model. So you have to really first figure out, did you fix the problem before you interpret each of the above tests. And I think that was all of the options we had then available here in this. So the mixed code then, could you have done proc mixed if you would have found that the variances were equal? And the answer would be yes. You would just delete this repeated statement and you would get a table where the results would match what we get in an analysis of variance. Okay, but it's really important that we test for unequal variances, again, because the unequal variances could be causing a lot of different things. And so at the time of the research project, if we may have different variances that occurred, perhaps due to different lab technicians, perhaps due to different days. Lots of things can cause that problem. So we want to make sure that we detect the true differences between the treatment level means and not detect just differences due to natural variability alone.